Okay, so this is chapter 3, section 2, and we're talking about logarithmic functions now. So you're probably more familiar calling them log functions, and that's what we'll refer to them as. Log functions are of the form y equals log with some base b and this value x here. Now your base value, your b here, cannot equal 1, and it needs to be greater than 0. And we can only work with things where this value here is greater than 0. So we can't take the log of a negative value or the log of 0. All right, now we can also write this in exponential form. That's b to the power of y equals x. And in order to convert back and forth from log form to exponential form, we would use the Snail rule here, and b to the power of y equals x. So this gives us b to the power of y equals x. Okay. Now these log properties that we see here, you should be pretty familiar with from Algebra 2. Log base b of 1, no matter what your base is, equals 0. Same thing with natural log. Log base b of b, if these two are the same, it's equal to 1. And then log base b of b to some power x is equal to x. And if I have some base b to the power of log base bx, and these two values are the same, then the answer is also x. So let's go ahead and work through some examples here. This first one says write in exponential form. So using the Snail rule, b to the power of 3 equals 27. Now a lot of people here are tempted to say b equals 3. That's not the answer. This is our answer. The question asked us to write it in exponential form. If that's what it's asking, this is your answer, not b equals 3. Now we can go the other way. We have log form right here, and whatever my base is, that's going to be the base in my log as well. And then here we'd have 15 to the power of something on the other side, so 2, and x here. And we can check our work to see if we did this correctly by using the Snail rule. 15 to the power of 2 equals x, and that's what we started with. In these next couple examples, we're just evaluating logarithms using the rules that we have above. So I'm going to try and keep both of them in the screen here. Now, log base 3 of 27. Because my base is 3, my thought is, can I rewrite this somehow? So log base 3 of 3 squared, or I'm sorry, 3 cubed, would be the same thing as 27. Well, then we can use this rule right here. If my base and this value are the same, then this would be my answer, 3. Looking at the next one, this looks really similar. I see the base, and I'd really like to make this have the same situation of the one we just had. Well, 1/5 is the same thing as 5 to the negative 1 power. We learned that with our exponent rules in chapter 1 and chapter 2. So looking at this here, what we can do is rewrite this as log base 5 of 5 to the negative 1 power. Now these two numbers are the same, so my answer is negative 1. In our next example, it looks very similar. I'm going to do some scratch work off to the side here. If I have 1 over square root 3, well, that's the same thing as 1 over 3 to the 1/2 power. But I don't want it as a fraction, I want it to be up here, so that's the same thing as 3 to the negative 1/2 power. Well, that's what I want now, since my base is 3. And so I can rewrite it like that. These two numbers are the same, so my answer is negative 1/2, and that's it. In the last one down here, we can do the same thing. Now this one is a little bit trickier to see. We don't want to turn 81 into 9, we want to turn 9 into 81. Well, 9 is the same thing as the square root of 81, which is the same thing as 9 to the 1/2 power. So what we can do then, or I'm sorry, which is the same thing as 81 to the 1/2 power. So what we can do then is say log base 81 of 81 to the 1/2 power, and then my answer would be 1/2. All right. Now, at the bottom here, we're making a note about the graphs of logarithmic functions. Now, log functions are inverses of exponential functions. They're inverses of one another. And if we remember that inverse functions have this special property with their points. The points just switch in order to find the inverse. So if I have, let's say, the point 3, -4 in the inverse, I have -4, 3 on that graph. And then we also have a little note here that natural log and e are inverses of each other as well. Okay. So I'm going to go ahead and flip the page and we're going to look at some of these graphs. So let's look at an example here. It says graph f of x equals 3 to the power of x and the inverse function. Well, we practiced graphing these in our last section, in section 1, and we used -1, 0, and 1. And plugging in -1, I have 1/3, plugging in 0, I have 1, and plugging in 1, I have 3. So let's go ahead and start with that. So I have -1 and 1/3, 0 and 1, 1 and 3. This is my graph here. And I have a horizontal asymptote right there. Now, for g of x, remember with inverses, you can just switch the points. So now I have 1/3, 1, and 3. And giving me 1/3, I'll get -1, 0, and 1. And so what I can do now is I can graph those points. So at 1/3, I had -1. At 1, I had 0. And at 3, I had 1. And this is the graph of the inverse. And the horizontal asymptote now becomes a vertical asymptote. So these are inverses of one another. And the special thing that we can see here is that it's a reflection across the line y equals x. So I'm going to turn my paper here just so we can see exactly how this looks. If you look at this yellow line here down the middle, these look exactly the same on both sides. And that's what happens with inverse functions. And so we can check and see if our graphs actually do look like a mirror image across the line y equals x. Now, there's a special relationship here with these points and what we chose to plug in here. So whatever my base is, that's going to determine what values I plug in here. I'll do 1 over my base, 1, and then whatever my base is. And that's going to always give me the output of -1, 0, and 1. Now let's do the same thing with natural log. So we said e to the power of x, plugging in -1, 0, and 1. Well, that gave us 1 over e, which was a little bit more than 1/3, so close to that. Plugging in 0 gave us 1, and plugging in 1 gave us e, which is about 2.7. So what I'm going to do here, and I'm actually going to change this. I don't like writing 1/3. I'm going to put 1 over 2.7. Okay. Now let's go ahead and graph that so far. So I have -1 is about right here, 1, and then 2.7. And that's my graph. And my horizontal asymptote. And then I can go ahead and I can graph my other function, which is g of x. And they switch. So I'm plugging in 1 over 2.7 or 1 over e, plugging in 1, and plugging in e. And I'm going to get out 1, 0, and negative 1. So let's go ahead and graph those points. So I have 1 over 2.7, and that's going to give me negative 1. Plugging in 1 gives me 0, and plugging in e, which is about 2.7, gives me 1. And this is the graph of the natural log function. I also have my vertical asymptote now at 0. And that's it. Those are those graphs. In calculus, we'll use a lot more of the natural log and log functions. In pre-calc, you'll see both. Okay. And going ahead and flipping the page, we can transform these graphs the same way we can transform everything else that we've looked at. So we've seen that we can shift things up, shift things down, shift things to the left, shift things to the right, reflect it across the x and y axis, stretch and shrink it horizontally. So those are all the same transformations that we saw in Chapter 1, Section 6. Now let's talk about the domain of a log function. We cannot take the log of a negative number or of 0. So the domain is whatever is going to make g of x greater than 0. And our range will always be from negative infinity to positive infinity. So you want to make sure that you know this right here. So let's talk about the domain and range of these functions right here. This first example, we want to make sure that what we have here is going to be greater than 0. Well, I know it's going to be greater than 0 because it's going to be squared. However, we can't let it equal 0 either. Now, there's a little note on the bottom here. If there's no number down here for the base, it's a base 10. So that means this is base 10. So we just want 7 minus x to not equal 0. So what that would mean is x cannot equal 7. Oops, not 0 here, 7. So my domain is negative infinity to 7, and then 7 to infinity. My range is negative infinity to infinity. For the next example, it's not squared, so it is possible that this could be negative. So we want x plus 6 to be greater than 0. So subtracting 6, x needs to be greater than negative 6. So my domain is going to be from negative 6 to infinity, and my range is going to be negative infinity to positive infinity. Now for these last little notes here, again, just a reminder, common logarithms, the term common logarithms just means base 10. And natural logarithms, you've seen ln x, that's just with a base e. All right? And that is the end of Chapter 3, Section 2.